Okay, hi. So let's continue with another theorem called the Rational Root Theorem, and this basically covers everything in terms of finding roots or zeros or x-intercepts, which can lead into factoring of the polynomial function. So here is the definition of rational root theorem. It's basically saying that if you have a polynomial function that is an integral polynomial function, that means that the leading coefficients for all of the terms are integers. And then if this has any roots, any zeros, any x-intercepts, and it looks like, and if it is in a form of x equal to a over b, that's a rational root, a over b. So if it does have any roots that looks like a over b, so a fraction where a is an integer, b is an integer, and as well b cannot be 0, obviously, then the a value comes from the constant term. So a comes from the constant term of the polynomial, and b comes from the factors of the coefficient of the highest degree term in that polynomial. Let me explain. So if we have suppose a over b is one of the rational roots, then in this case your a is the factors of constant term. That's your a. So comes from the factors of constant term, okay? And your b comes from the leading coefficient of the highest degree term, okay? So that's what's happening here. These are factors. So we need to write up all the factors of, both a, let's do factors of a, and in this case will be plus or minus 1 plus or minus 3. Okay, so that would be the a right there. And then let's write up all the factors of b. That's the leading coefficient, so that would be again plus or minus 1 plus or minus 2. So based on the rational root theorem and the integral root theorem, we know that we can go through, and if we do the a over b, that will cover basically every single rational root we have. Remember, a rational root is a over b. B can be 1, and if b can be 1, it just becomes an integer. All right, so that's okay. There's nothing wrong with that. So what are the possibilities for the rational root that looks like a over b? So let's write up the a over b now based on what we have here. So remember, that is your a, and we have a b, okay? A over b. So we're going to start with the 1. So that would be plus or minus 1 over 1. So basically you're going to get plus 1 minus 1. That's what you're going to get. Okay, so those are the two possibilities. Next one would be plus or minus 1 over 2, because 1 divided by 2, it would be 1/2, and we have to take both positive and negative. Okay, the next piece is that we got to do the 3, so it would be plus or minus 3 over plus or minus 1, which will end up being again plus or minus 3. Okay, and then the last piece would be plus or minus 3 divided by 2, and we can say plus or minus 2, but it doesn't really matter, because at the end of the day you're going to have plus or minus 1 plus or minus 1 over 2 plus or minus 3 and plus or minus 3 over 2. These are all the rational roots that you could possibly have for this polynomial function. Now we know from the integral root theorem that we ended up getting, we've done this question before, and when you use the factor theorem, okay, the factor theorems, when you use that, so we go through each of these f of 1 and then f of -1. Remember the factor theorem. If we do this and the remainder is 0, then that means that has to be our root. So we went through all of this, and you notice that, by the way, and more, right? So f of, and then you have to keep doing that. So you do f of 1/2, f of -1/2, and then you do the same thing again, f of 3, f of -3, and when you plug all of these, and then the last piece is the let's do the f of 3/2 and f of -3/2. Okay, when you do all of this, at the end, the ones that equal to 0, those will be your roots. We know that f of -1 was 0. We know that. We've done this. We also know that f of 3 was 0. So those two we know. And we also know that this function, polynomial function, is a degree 3 function. So that's a degree 3. What does that mean? What is the maximum number of zeros? The maximum number of zeros will be 3. Only 3 x-intercepts. So we need one more. And when we did that, you plug in one of the fractions, 1/2 and -1/2, because those are the only two integral roots we got. So the other possibilities will be the fraction. And in this case, what will happen is that when you solve this, you notice that f of 1/2 will be equal to 0. Okay, and that is it. And then the roots are, these are the roots, will be, we have 1/2, we can have -1, and we also have 3. Okay, so right here, these are the roots, right there, and then right there. Okay, factors will be x plus 1, x minus 3, and 2x minus 1. That is your factor form of that polynomial function. This is called the rational root theorem, where each of those will give you the roots, the x-intercepts, and then obviously in the factor form you plug it in, and these are the factors of the polynomial function. When you graph this, what will happen is that the graph that you will have, it will go through x equals to -1, x equals to 3, and x equals to 1/2. The graph will go through each of those. So now let's look at the graph. So here is the original polynomial function we had. I graphed it using Desmos, and notice that it goes through just like that. And look at the zeros, -1, 0.5, and 3. Now, and then I put it in a factor form because we found the factors using the factor theorem, and based on that, remainder theorem, and then rational root theorem. Okay, so if I click on that and engage that graph, it's the same graph. It doesn't change. It does not change the graph. It's exactly the same. So if I change that, look at that, what happens. It's the same thing again. So the new graph will end up being the same. The zeros are the same in the factor form, the other one is not. Roots means x-intercepts of the graph. And that is the very important information for any polynomial function. Okay.